November 10th, 2025. Observatories around the world are reporting a phenomenon that challenges everything we've observed about interstellar objects. 3i Atlas, already notable for its unusual trajectory and composition, has just displayed behaviour that no comet, no known interstellar body has ever demonstrated. High-resolution telescopes recorded a sudden surge in brightness, accompanied by an unexpected shift in its orbital path. Initial data suggest that the object's rotation is changing, a phenomenon that cannot be explained by conventional cometary physics alone. Spectroscopic analysis reveals volatile emissions that do not match any previously catalogued pattern, and the distribution of dust along its tail defies all existing models of solar interaction. For scientists tracking 3i Atlas, the implications are immediate and unsettling. Every measurement, every frame of imagery, points to an object that is not just unusual. It is actively rewriting the rules we thought governed interstellar visitors. Instruments from Chile to Hawaii are converging on the same data, a brightening that is localized, directional, and intensifying in ways that defy prediction. It is precise, measurable, yet entirely unexpected. As one possibility fades, another emerges. The data are consistent yet contradictory, pointing simultaneously to known physics and to something wholly uncharted. And this is where the story turns. Over the next 15 chapters, we will examine each facet of 3i Atlas's behaviour, explore the evidence, and follow the unfolding anomalies in real time, layering observation with analysis until the full scope of this interstellar enigma begins to emerge. Since the earliest detection of 3i Atlas, its trajectory has been under constant scrutiny. Unlike typical comets entering the inner solar system, which follow predictable elliptical paths shaped by gravitational interactions, 3i Atlas exhibits deviations that are both subtle and profoundly consequential. Observatories equipped with precision astrometry have charted its position over the past several months, noting a series of small but cumulative changes in velocity and inclination. These shifts are not random. They are directional, suggesting either an internal force influencing the object or interactions with phenomena that remain largely unseen. The latest data indicate a sudden deviation in its orbital arc. At first glance, the difference seems minor, a fraction of a degree, but even the smallest change in trajectory has enormous implications when projected over interstellar distances. A shift this precise, occurring over a timescale of days rather than decades, challenges established models of cometary dynamics. Traditional explanations, such as outgassing-induced thrust or solar radiation pressure, fail to account fully for the observed acceleration vectors. The timing, magnitude, and consistency of these shifts imply either an unprecedented physical process within the comet or a subtle external influence that has yet to be detected. To contextualize this, consider the mechanics of cometary motion. Comets are composed primarily of ice, dust, and organic compounds, loosely held together in a fragile matrix. As they approach the Sun, heating causes volatile compounds to sublimate, creating jets that can slightly alter their rotation and path. This is well documented, and yet 3i Atlas exceeds these effects by orders of magnitude. High-precision modelling shows that the observed trajectory changes cannot be replicated even when all known outgassing effects are amplified to extreme theoretical limits. Astrophysicists have cross-verified the data using multiple observatories, including the Very Large Telescope in Chile, the Mauna Kea observatories in Hawaii, and radar tracking from facilities in Europe. Each data set independently confirms the anomaly. Using these measurements, researchers have recalculated orbital elements, revealing a consistent acceleration toward a vector that was previously unaccounted for in simulations. This vector does not align with solar radiation pressure, does not correspond with known gravitational perturbations from planets or minor bodies, and remains unexplained by conventional models. What makes this trajectory particularly compelling is its predictive consequences. Projected forward, even minor deviations today will translate into vastly different positions and velocities within weeks and months. Accurate forecasting of 3i Atlas's path is therefore extraordinarily challenging, complicating efforts to schedule targeted observations, especially as it approaches perihelion. Every new observation must be rapidly integrated into models to prevent cumulative errors, and yet, even with continuous updates, the object defies fully deterministic prediction. the broader implications extend beyond 3I Atlas itself. If an interstellar object can undergo directional acceleration that cannot be accounted for by known mechanisms, it raises questions about the forces acting in interstellar space. Are we observing a unique internal mechanism within 3I Atlas, a previously unknown type of outgassing, or some interaction with particles, fields, or matter that has yet to be detected? The anomaly forces a reconsideration of what interstellar objects are capable of, and whether our current classification systems adequately encompass such phenomena. In parallel, astronomers have begun to analyse historical data for subtle precedents. No comet recorded in the past century exhibits this combination of precise acceleration, trajectory shift, and sustained directional deviation. Even interstellar visitors such as Oumuamua, which sparked debate over its non-gravitational acceleration, do not fully match the pattern observed here. Whereas Oumuamua displayed a consistent push, 3I Atlas shows variations that are localized along its orbit, suggesting complex internal or external forces that vary with position relative to the Sun. Adding another layer of complexity is the interplay between trajectory and rotation. Data from photometric monitoring indicate that changes in spin rate coincide with periods of orbital deviation. This raises the possibility that rotational torques are influencing its motion in ways that standard cometary physics cannot explain. Yet these torques do not correspond to the expected patterns of asymmetrical outgassing, leaving the origin of the forces uncertain. The stakes of understanding this trajectory anomaly are high. Accurate modelling is not merely an academic exercise. Interstellar objects passing through the solar system offer a rare opportunity to study primordial matter from beyond our planetary system. Misjudging its path could result in missed observations during critical windows, particularly as 3I Atlas approaches regions of high observational value near perihelion. Each new deviation must be interpreted in real time, balancing known physics with the possibility of entirely new phenomena. At this stage, researchers are considering several hypotheses. Some posit an internal structural irregularity, perhaps a subsurface cavity causing sudden jet expulsions. Others suggest interactions with microscale interstellar fields, dust, or plasma streams might produce a minute but cumulative force. Each hypothesis comes with constraints and unresolved questions, and none fully account for the precise pattern of observed motion. Yet this evidence raises new scientific questions. If internal forces are sufficient to alter trajectory so dramatically, what does that imply about the composition, density, and cohesion of 3I Atlas? If external forces are at play, what unknown elements of interstellar space are we only now detecting? Every calculation, every adjustment of orbital parameters emphasizes that 3I Atlas is not following a conventional path. Its motion is an enigma, and it is precisely this unpredictability that demands intense observation and rigorous analysis. In the coming chapters, we will layer additional anomalies atop this trajectory puzzle. Sudden brightness surges, unusual dust emissions, and chemical compositions that challenge prior expectations. Each piece of evidence compounds the mystery, building a picture of an interstellar object that is more complex, more active, and more anomalous than anything previously documented. But one question remains unanswered. What mechanism could drive such a precise, variable, and sustained deviation in motion, all while maintaining structural integrity in the harsh environment of the inner solar system? The answer will require integrating orbital mechanics, spectroscopic data, and real-time observational analysis, a challenge that will continue to push the boundaries of our understanding. Alongside its unusual trajectory, 3I Atlas has displayed a remarkable surge in brightness over the past several weeks. Observers first noticed the change on November 3rd, 2025, when automated photometric systems detected an unexpected increase in luminosity. Unlike typical comets, whose brightness gradually increases as they approach the Sun due to predictable sublimation of ices, 3I Atlas brightened rapidly and unevenly. Within the span of just 48 hours, its apparent magnitude shifted by nearly 2 full points, a deviation that exceeds the standard rate for comets at a similar heliocentric distance. The data were confirmed independently across multiple observatories. The Pan-STARRS telescope in Hawaii measured a rapid increase in reflected light in the visible spectrum, while the Hubble Space Telescope captured detailed imagery showing localized bright patches on the surface. Infrared instruments recorded corresponding heat emissions, suggesting that the brightness was not merely a reflection effect, but indicative of active physical processes on or near the surface. Analysis of the light curve reveals irregularities that are unprecedented. Unlike the smooth, sinusoidal variations typically seen in comet brightness, caused by rotation and jet activity, 3I Atlas exhibits erratic spikes in intensity. These spikes are directional, localized to specific regions of the nucleus, and repeat at intervals that do not match the measured rotation period. In other words, the brightening is not simply a function of rotation exposing reflective surfaces. It appears to be driven by discrete events, potentially energetic releases from within the object itself. Spectroscopic data collected during these periods of brightening provide additional clues. Emission lines of cyanide, diatomic carbon, and a range of volatile organics are sharply elevated, suggesting that the brightening is associated with sudden outgassing events. Yet the ratios of these compounds differ from what would be expected in a typical cometary coma. Carbon monoxide and water vapor emissions are unusually weak relative to the intensity of the visual surge, implying that the source of energy behind these events may involve more exotic processes than simple ice sublimation. One hypothesis gaining traction is that microfractures within the surface layers of 3I Atlas periodically release stored energy, causing bursts of both gas and dust. This theory is supported by high-resolution imagery that shows transient plumes emanating from localized depressions on the surface. These plumes appear and fade within hours, correlating with peaks in brightness and minor adjustments in trajectory. Such episodic activity is consistent with a nucleus that is structurally heterogeneous, containing cavities or volatile-rich pockets that respond unpredictably to thermal stress. Comparisons with previous interstellar visitors highlight just how extraordinary this behavior is. Oumuamua exhibited no detectable coma and only hinted at non-gravitational acceleration, while typical solar system comets display gradual, predictable brightening patterns. 3I Atlas, by contrast, behaves as though it is actively modulating its own luminosity, a process that cannot be fully explained by conventional physics. Each spike in brightness carries an implicit signature of mass ejection, rotation, and localized activity, parameters that must be reconciled with the anomalous trajectory described earlier. Observers have also noted an unusual asymmetry in the brightening pattern. Plumes are not evenly distributed across the nucleus, nor do they appear to be linked solely to solar-facing regions. This raises the possibility that internal processes, perhaps even subsurface heating or chemical reactions, are driving activity independently of direct solar radiation. If correct, this would represent a fundamentally different mode of cometary physics, one in which internal dynamics play a dominant role in shaping observable behavior. Thermal modeling reinforces the peculiarity. Temperature readings across the surface, taken with mid-infrared instruments, show localized hotspots that fluctuate more rapidly than expected. The nucleus does not appear to heat evenly, and the distribution of these hotspots does not correlate perfectly with either illumination angle or rotational phase. This indicates that 3I Atlas is an object in constant uneven flux, where energy is released sporadically and locally, producing the sudden brightness surges we now observe. The implications extend beyond simple observation. Brightness surges can influence trajectory through a process known as reactive thrust, where mass ejection imparts momentum to the nucleus. In the case of 3I Atlas, each surge may contribute to the deviations recorded in Chapter 1. This feedback loop, where outgassing alters trajectory, which in turn changes solar exposure, potentially triggering further brightening, is a complex dynamic system that challenges our ability to predict future behavior. Importantly, the brightness increase also affects our observational capabilities. As the object becomes more luminous, finer structural details are revealed, allowing astronomers to detect small-scale jets, fractures, and plume formations. However, higher brightness can saturate certain instruments, complicating precise measurements and requiring careful calibration. Observatories must coordinate closely to ensure that data remain comparable across different instruments, and that transient events are captured comprehensively. Each burst of brightness is also an opportunity for chemical analysis. Spectral resolution allows scientists to track volatile composition in near real time, providing insight into the object's interior makeup. Already, the data hint at a composition that may include highly volatile compounds previously undocumented in comets, along with complex organics that challenge existing models of interstellar matter. The pattern of emissions suggests not random dispersion, but structured release, hinting at a nucleus that may be far more active and internally complex than any solar system comet. Yet for all the data, many questions remain. Why does 3I Atlas release energy in discrete high-intensity events rather than gradually? Are these surges linked to structural anomalies within the nucleus, or are they influenced by unknown external forces? And how do these events interact with the trajectory shifts that have already confounded predictions? Each brightness surge not only illuminates the surface of the comet, but also casts light on the limits of our understanding, forcing scientists to reconsider foundational assumptions about interstellar objects. The pattern is both consistent and contradictory, repeatable yet unpredictable, measurable yet enigmatic. Brightness alone cannot explain all observed anomalies, but when combined with trajectory, rotation, and outgassing data, it forms a multi-layered puzzle, each layer reinforcing the sense that 3I Atlas is not a conventional comet. It is an interstellar object with a complex active interior capable of processes that challenge the boundaries of observational astronomy. The sudden brightening of 3I Atlas is only part of the story. Accompanying these luminosity surges are complex patterns of dust emission, forming plumes and tails that defy conventional cometary models. Observatories equipped with high-resolution cameras and polarimetric filters have captured fine details of these emissions, revealing streams of particulate matter that are not uniformly distributed. Instead, the dust is ejected in jets, arcs, and asymmetric clouds, each pattern seemingly tied to localized surface activity. Dust emission is a common feature of comets. As volatiles sublimate, they carry embedded dust grains into space, forming the coma and eventually the tail. However, the dust from 3I Atlas exhibits properties that are anomalous in several respects. Grain size distribution is broader than expected, spanning from micron-scale particles to centimeter-sized clumps. Spectral analysis shows that some grains reflect light in ways inconsistent with standard silicate or carbonaceous compositions, suggesting a complex mixture of materials, including rare interstellar compounds. These unusual compositions may indicate that the object preserves primordial interstellar matter, largely unaltered since its formation. The structure of the dust jets is equally perplexing. Observations show that emissions are not evenly spaced around the nucleus, nor do they align predictably with rotation. Instead, they appear to originate from discrete transient vents or fissures. Some jets are short-lived, dissipating within hours, while others persist for days, stretching tens of thousands of kilometers into space. The orientation of these jets often shifts in ways that suggest either subsurface redistribution of volatiles or the influence of external forces such as magnetic fields or charged particles in the solar wind. Polarimetric measurements provide further insight. By analyzing the polarization of scattered light, astronomers can infer particle size, shape, and surface texture. In the case of 3I Atlas, the polarization data indicate irregular, elongated grains, many with fractal-like structures. Such morphologies are rarely observed in typical solar system comets, which tend to emit more spherical or compact grains. The irregularity of these particles may contribute to the unpredictable scattering of light, amplifying the observed brightness surges and further complicating efforts to model the object's behavior. The dust emissions also interact dynamically with the comet's trajectory. The release of mass through jets exerts tiny forces on the nucleus, altering its path in subtle but measurable ways. This phenomenon, known as non-gravitational acceleration, is well documented in solar system comets, but in 3I Atlas, the effect appears unusually strong and variable. Observed correlations between jet activity, brightness surges, and trajectory deviations suggest a feedback loop. Localized emissions change the object's rotation or motion, which in turn influences the next emission event. This self-modulating system creates a level of complexity rarely seen, even in the most active comets. High-resolution imagery has also revealed fine structural details of the dust itself. Clumps and filaments are visible, some forming spiral patterns around the nucleus, indicative of rotational influence, while others extend radially, as if expelled by sudden explosive forces. These structures provide a record of the internal dynamics of the nucleus, revealing regions of differential activity, variable composition, and potentially hidden subsurface features. Some filaments appear to originate from areas that have undergone recent fracturing, suggesting that mechanical stress may play a role in releasing both dust and volatiles. Observations in multiple wavelengths add another layer of understanding. Infrared data reveal that certain dust clouds are warmer than the surrounding Coma, implying that the grains may carry embedded energy or experience localized heating. Ultraviolet measurements show emissions from excited molecules adhering to the grains, confirming the presence of volatile compounds that survive ejection into space. The combined data indicate a highly heterogeneous system. Dust, gas, and energy are all released in discrete interacting events, each influencing the others. The pattern of asymmetry in the dust emission is particularly striking. Whereas most comets produce tails aligned along the Sun-Comet line or swept back by solar wind, 3I Atlas frequently develops jets and plumes at angles inconsistent with either radiation pressure or rotational axis. These deviations suggest that internal structure, variable activity, and possibly external forces are all contributing. In some observations, jets appear to switch on suddenly, creating arcs of dust that persist for hours before dispersing. Such behaviour points to a nucleus with complex thermal and mechanical properties capable of rapid, localized energy release. The implications of these dust patterns extend beyond 3I Atlas itself. By examining the composition, structure, and dynamics of emitted particles, astronomers can infer the internal structure of the nucleus, the processes driving activity, and even clues about the environment in which the object formed. The presence of unusual grains, the variability of emissions, and the asymmetry of the jets all suggest that this is not a typical comet. It is an interstellar object with a complex, evolving surface, influenced both by internal mechanisms and the space environment it traverses. These emissions also provide a tangible link to other observed anomalies. The correlation between dust jets, brightness surges, and trajectory shifts strengthens the emerging picture of 3I Atlas as a self-modulating, highly active body. Each event is measurable, yet unpredictable, creating a dynamic system in which small internal changes can propagate outward, affecting both observable properties and motion through space. The data collected from this ongoing activity not only inform our understanding of 3I Atlas, but challenge conventional cometary physics, suggesting mechanisms that may not have been observed in our solar system before. Finally, the dust patterns raise questions about stability. The repeated ejection of large volumes of material could alter the nucleus over time, potentially weakening structural integrity or changing rotational dynamics. Observing these patterns over weeks and months allows scientists to monitor how the comet adapts, revealing its resilience or vulnerability. The interplay between emission, rotation, and trajectory creates a feedback loop that is crucial to understanding the behaviour of this interstellar object. As we prepare to examine the next layer of evidence, the focus will shift to gas composition, a critical factor that complements the dust data. By analysing the specific volatiles being released, their ratios, and their temporal fluctuations, we gain deeper insight into the chemical and physical processes driving 3I Atlas's extraordinary activity. The story of dust is only part of a larger system of interacting forces that make this object one of the most compelling interstellar mysteries observed to date. While dust emission provides a visible record of 3I Atlas's activity, the true complexity of the object is revealed through its gaseous composition. Spectroscopic analysis allows scientists to identify the molecular makeup of the Coma, offering insight into both surface and subsurface processes. Observations over the past several weeks reveal a mix of volatile compounds, some expected in cometary physics, others entirely anomalous. Water vapour, a staple of solar system comets, is present, but in surprisingly low concentrations relative to the intensity of the dust and brightness surges. Carbon monoxide is detected intermittently, often correlating with the appearance of transient plumes, but its ratio to other volatiles is inconsistent with standard sublimation models. More strikingly, spectral lines indicate the presence of complex organic compounds, including hydrocarbons and nitriles, in quantities higher than typically seen in comets, originating within our solar system. Some of these molecules are highly reactive, suggesting that they are either freshly exposed from the interior or continuously replenished through internal chemical reactions. The spatial distribution of gases is equally intriguing. Observations from ground-based telescopes and spaceborne instruments show that emissions are not uniformly expanding from the nucleus. Instead, they are concentrated in localized regions, often coinciding with dust jets and areas of sudden brightening. This patchy distribution implies that 3I Atlas has discrete reservoirs of volatiles beneath its surface, released episodically rather than gradually. Certain emissions are short-lived, appearing for hours and then vanishing, while others persist for days, forming temporary clouds in the Coma. Temperature-dependent reactions may explain some of these variations. Spectroscopic measurements in the infrared and ultraviolet suggest that volatile compounds are released when localized heating reaches critical thresholds. However, thermal modeling indicates that solar heating alone cannot account for the timing or intensity of these events. The localized spikes in gas production appear to involve internal energy sources or subsurface processes that are not yet fully understood. The detection of previously rare or undetected molecules adds another layer of mystery. Traces of ammonia, methanol, and small organosilicon compounds have been identified, each in proportions that do not conform to predictions based on solar system comet models. Their presence points to a chemical environment markedly different from the icy bodies we're familiar with, hinting at formation in a region with unique conditions or subsequent processing during interstellar travel. These findings suggest that 3I Atlas may serve as a time capsule of chemical processes from another star system, offering a glimpse into the diversity of molecular clouds beyond our own. Temporal correlation between gas emissions and brightness surges further reinforces the link between physical activity and chemical processes. Peaks in the emission of specific molecules coincide with sudden brightening events, suggesting that the release of gas may drive luminosity changes by altering the reflectivity of dust-laden jets or by energizing surrounding material. In some instances, emissions appear to precede visible outbursts, hinting at a cause and effect relationship where internal gas pressure builds until the surface fails, releasing both volatiles and particulate matter. Isotopic ratios provide additional clues to the origin and evolution of 3I Atlas. Preliminary measurements of carbon and nitrogen isotopes show deviations from solar system norms, consistent with interstellar formation. These ratios are not uniform across all emissions, suggesting that different regions of the nucleus may have preserved materials from distinct environments or formation epochs. Such heterogeneity indicates a complex internal structure, and may help explain why certain areas of the nucleus exhibit more vigorous activity than others. The relationship between gas and dust is critical to understanding the object's overall behaviour. Gas emission exerts a small but measurable force on the nucleus, contributing to the trajectory shifts observed in Chapter 1. The interaction between volatile release, dust ejection and rotation forms a tightly coupled system. Localized bursts of gas can propel dust streams, which in turn modify the comet's orientation and motion. These interdependent dynamics create a feedback loop, making predictive modelling extraordinarily challenging. High-resolution spectrographs have also detected transient compounds that exist only briefly in the Coma, appearing and disappearing within hours. These short-lived species suggest active chemical reactions occurring in real time, potentially triggered by exposure to sunlight or internal heat. Such processes have not been documented in solar system comets to this degree of rapidity, raising questions about the chemical stability of interstellar bodies during their transit through warmer stellar systems. The gas composition provides clues about the internal structure of the nucleus as well. Regions that produce high levels of volatile compounds are often associated with areas of recent structural change, such as fissures, pits, or fracturing. This supports the hypothesis that the nucleus contains a heterogeneous mix of ice, dust, and organic material, with pockets of volatile-rich compounds that can trigger episodic outbursts when exposed. Understanding this internal architecture is crucial for interpreting the interplay between chemical activity, dust emissions, and trajectory anomalies. By combining spectroscopic data with photometric and dust measurements, a pattern emerges. 3. The Atlas is not a passive, inert body. It is actively interacting with its environment, releasing material in complex and highly variable ways. The chemical signals are both indicators and drivers of its observed behaviour, linking surface processes to the broader anomalies in motion, brightness, and emission patterns. This chemical complexity challenges existing cometary models and emphasizes that interstellar objects may follow a wider spectrum of physical behaviors than previously assumed. Yet significant questions remain. Why does 3I Atlas contain such an unusual mix of compounds, and what does this imply about its formation environment? Are the episodic gas releases driven solely by thermal and mechanical stress, or is there a chemical feedback mechanism internally regulating activity? How does this chemical activity influence the trajectory and structural integrity of the nucleus over time? These questions form the bridge to the next layer of analysis: spin dynamics, where rotational behavior interacts with both gas and dust emissions to produce some of the most perplexing anomalies yet observed. Observations of 3I Atlas reveal irregular rotational behavior that challenges conventional understanding of cometary physics. Photometric monitoring shows variations in light curves that cannot be attributed solely to shape or surface albedo. The rotation period is fluctuating, and the axis of rotation is shifting unpredictably. The data suggests that the nucleus is undergoing complex spin dynamics, influenced both by internal forces and by material ejection. High-resolution imaging indicates that jets of gas and dust are not only localized but are also asymmetrically aligned with respect to the nucleus's rotation. When material is expelled, the resulting reactive torque subtly alters the spin rate. These changes are small on human timescales, but significant over days and weeks, introducing a cascading effect on the object's orientation and the distribution of surface heating. Areas previously exposed to sunlight may become shaded, triggering localized cooling, while other regions experience renewed stress and sublimation. The rotation appears to exhibit precession, with the spin axis gradually wobbling. This wobble is irregular in both magnitude and direction, suggesting that internal density variations, subsurface cavities, or structural weaknesses are affecting rotational stability. The combination of uneven mass distribution and episodic material ejection produces a dynamic system in which the nucleus continuously adjusts, sometimes subtly, sometimes dramatically, to maintain equilibrium under changing conditions. Measurements from radar and optical tracking indicate that rotation rates fluctuate on timescales of hours to days. Sudden increases in angular velocity coincide with bursts of outgassing, while slower rotations follow periods of quiescence. The timing and magnitude of these variations do not correspond to solar illumination alone, implying that internal mechanisms are generating forces capable of modifying spin in a controlled yet unpredictable manner. Rotational dynamics directly affect the observed morphology of the Coma and dust emissions. Jets align along rotational axes or emerge tangentially, creating spiral patterns in the surrounding dust clouds. In several instances, localized eruptions on the surface appear to shift the spin axis, redirecting jets in ways that contribute to asymmetries in the tail. The interplay between spin and mass ejection produces a feedback loop. Rotational shifts expose new regions to sunlight, triggering sublimation or fracturing, which in turn further modifies rotation. The irregular spin also influences trajectory. Reactive forces generated by asymmetric outgassing are magnified when the nucleus rotates unpredictably, leading to non-linear deviations from the expected orbital path. These rotationally induced trajectory changes coincide with the anomalous accelerations recorded by observatories, suggesting that spin dynamics are a key driver behind the object's unusual motion. Internal stresses from rotation may be contributing to structural changes within the nucleus. Surface fractures, fissures, and occasional small collapses are observed in regions experiencing high rotational torque. These events release gas and dust, adding another layer of complexity to the dynamic system. The nucleus behaves as a coupled physical and chemical system, where spin, material properties, and internal energy interact continuously to produce measurable effects. Thermal modeling supports the observed dynamics. Uneven rotation alters the distribution of sunlight across the surface, creating localized heating and cooling cycles. These cycles can trigger sublimation in volatile-rich pockets, which amplifies jets and introduces additional torque, reinforcing spin irregularities. This self-modulating mechanism allows the nucleus to adapt dynamically to external conditions, while simultaneously producing phenomena that appear chaotic from an observational perspective. Magnetohydrodynamic considerations may also play a role. Charged particles within jets interact with solar wind and local magnetic fields, potentially influencing rotation at microlevels. While these forces are small, their cumulative effects over time could contribute to subtle variations in spin. particularly when combined with irregular mass distribution and episodic ejection events. The consequences of this spin behavior are profound. Variability in rotation affects the timing and location of active regions, alters the direction and intensity of jets, and compounds trajectory anomalies. The interconnectedness of rotation, gas, and dust forms a dynamic system where small variations propagate through multiple channels, producing emergent behavior that challenges conventional cometary physics. The nucleus exhibits rotational resilience despite repeated perturbations, suggesting a structural integrity capable of withstanding asymmetric forces. Yet the complexity of the system implies ongoing adaptation, with rotation, mass ejection, and surface activity co-evolving continuously. The patterns observed are measurable, yet irregular, reinforcing the notion that 3I Atlas is an object operating at the limits of known physical behavior for cometary and interstellar bodies. Observations show that 3I Atlas responds to the Sun in ways that defy conventional models of solar system comets. As it approaches perihelion, solar radiation does more than simply drive sublimation. It interacts with the nucleus in localized, uneven patterns, producing intense thermal gradients across the surface. Temperature measurements indicate that some regions heat far more quickly than surrounding areas, creating hotspots capable of triggering sudden jets of gas and dust. These energetic plumes are not uniformly distributed, suggesting that surface morphology, internal composition, and solar angle combine to produce highly variable responses. The solar wind further complicates the environment. Charged particles streaming from the Sun interact with ionized gases in the Coma, generating electromagnetic forces that subtly influence the trajectory and rotation of the nucleus. In certain regions, magnetic field lines appear to align temporarily with active jets, producing visible curvature in the emitted dust streams. These interactions vary over time, depending on both solar activity and the orientation of the nucleus, creating dynamic, sometimes unpredictable patterns in the surrounding Coma and tail. Spectroscopic observations show that solar heating triggers selective sublimation of volatile compounds that remain inert in shaded areas suddenly vaporize under direct sunlight, producing bursts of gas that coincide with localized brightening. The combination of variable insolation, internal structure, and rotational irregularities produces a patchwork of activity across the nucleus, with some regions experiencing continuous outgassing while others remain dormant. Thermal expansion and contraction also play a role. As the surface cycles between heating and cooling, stress fractures develop, occasionally exposing subsurface volatile-rich layers. These fractures can precipitate explosive eruptions of material, launching dust and gas into the Coma at velocities exceeding predictions based on standard sublimation models. The irregularity of these events reinforces the pattern of unpredictability, with each exposure creating new active regions and modifying rotational dynamics. The tail exhibits unusual structural features influenced by solar interaction. Observations in multiple wavelengths show that the ion tail is sometimes kinked or bifurcated, deviating from the expected orientation along the Sun-Comet line. Charged dust particles interact with both the solar wind and local magnetic fields, producing transient structures that can persist for hours or days. These deviations indicate a complex interplay between ejected material, solar forces, and the object's own variable rotation. The magnitude of solar influence also affects long-term trajectory. Repeated bursts of sublimation, combined with asymmetric jets, create reactive forces that gradually alter the orbital path. These small cumulative effects contribute to the anomalous accelerations observed, compounding the challenges of predicting 3I Atlas's motion. Solar proximity thus acts not only as an energy source, but as a dynamic environmental factor, shaping both observable phenomena and underlying physical behavior. Temperature mapping of the nucleus reveals that solar energy penetrates unevenly, with some subsurface pockets absorbing heat more efficiently than others. These zones appear to correspond with regions of repeated outgassing, suggesting that internal heterogeneity governs response to sunlight. The interaction of thermal energy with volatile-rich pockets creates localized pressure differentials, often resulting in the sudden release of material observed as dust jets and brightness surges. Solar-induced electrical phenomena may also be present. Charged particles in jets interacting with the solar wind can generate microelectric fields, which could influence particle motion and even the dynamics of the gas release. While these forces are subtle, they may contribute to the fine-scale deviations in jet orientation and tail morphology observed in high-resolution imagery. The interplay between solar forces, rotational dynamics, and internal structure forms a complex system of feedback loops. Localized heating triggers jets which modify rotation. Changes in rotation alter exposure to sunlight, which in turn affects future outgassing. These interconnected processes make 3I Atlas a highly dynamic object, with solar interaction serving as both catalyst and amplifier of the irregular behavior observed. Evidence of solar interaction is further reinforced by temporal correlations. Observations show that brightening events and dust emissions increase during periods of peak solar exposure, yet the response is highly variable, indicating that internal factors are modulating how energy is released. The nucleus does not respond uniformly. It behaves as a heterogeneous system in which solar energy is filtered through complex structural and compositional layers, producing measurable but unpredictable outcomes. High-resolution spectroscopy also reveals that solar proximity triggers selective chemical reactions. Certain volatile molecules appear transiently, likely generated through photolysis or thermal activation, creating short-lived species detectable only during intense exposure. These transient compounds may contribute to observed changes in luminosity, jet activity, and the composition of ejected dust, reinforcing the interdependent nature of solar interaction, chemical processes, and mechanical behavior. The combined observations indicate that the Sun is not simply an external heat source, but a dynamic agent shaping the behavior of 3I Atlas in real time. Thermal, chemical, and electromagnetic interactions, amplified by the nucleus's irregular rotation and internal heterogeneity, produce the complex and often unpredictable phenomena captured by observers. The solar environment is a lens through which the object's internal processes become visible, revealing patterns of activity that are as precise as they are anomalous. Observations of 3I Atlas gain additional significance when compared to historical records of interstellar and extreme cometary bodies. Over the past century, a handful of objects have entered the solar system from beyond, each revealing properties that challenge conventional expectations, yet none display the combined anomalies now evident. Oumuamua, the first confirmed interstellar object, exhibited non-gravitational acceleration, but lacked a detectable coma or tail, leaving the mechanism driving its motion uncertain. Its elongated shape and apparent lack of volatile emission made it an enigma, but its behavior was relatively uniform compared to 3I Atlas. Borisov, the second interstellar visitor, demonstrated a more conventional cometary signature, with gas and dust emissions consistent with solar heating and typical comet chemistry. Its activity, while informative, followed predictable physical models, allowing astronomers to reconcile observed behavior with established theories of comet formation and interstellar travel. In contrast, 3I Atlas presents a combination of properties not previously recorded. Its trajectory shifts are larger and more irregular than those inferred for prior interstellar objects. Brightness surges occur on shorter timescales and with greater intensity than any previously observed. Dust emissions and jet orientations are asymmetrical and inconsistent with either rotational phase or solar radiation vectors. Spectroscopic data reveal chemical compositions that diverge sharply from known comets, including volatile-rich regions and transient compounds that suggest active chemical processes. The combination of rotational irregularities, solar interactions, and unpredictable outgassing creates a system of anomalies far exceeding the precedent set by historical observations. Past comets with unusual activity, such as Comet 29P/Schwarzmann-Wachmann, showed episodic outbursts, yet these events were largely predictable and confined to specific heliocentric distances. They lacked the simultaneous complexity of trajectory anomalies, chemical diversity, and spin irregularities now documented for 3I Atlas. Even comets exhibiting fragmentation or surface collapses maintain predictable mass loss patterns, whereas 3I Atlas displays discrete, localized emissions that defy simple classification. Archival data reinforce the uniqueness of 3I Atlas. No records indicate an object with this level of heterogeneity, where chemical composition, dust ejection, rotational dynamics, and trajectory variation all interact in measurable but unpredictable ways. Historical models of comet physics assumed relatively homogeneous nuclei, responding primarily to solar heating. 3i Atlas demonstrates that interstellar objects can exhibit far more complex adaptive behaviour, responding simultaneously to internal structure, external forces, and dynamic feedback loops. The historical context also highlights the implications for observational strategies. Previous interstellar objects were rare and often poorly characterized due to limited data, constraining predictive modeling. 3i Atlas, by contrast, is being observed continuously with a global network of instruments, revealing details at a level unprecedented in the study of interstellar bodies. This wealth of data underscores how exceptional its behavior is, as anomalies that would have gone unnoticed in prior cases now appear clearly and consistently across multiple independent observations. Comparisons extend to tail morphology as well. Historical comets with strong solar interaction show well-defined ion and dust tails aligned with radiation and wind forces. 3i Atlas, however, produces tails and jets that deviate significantly from these patterns, exhibiting curvature, bifurcation, and localized density variations inconsistent with standard solar-driven models. The divergence in tail behavior emphasizes that structural and compositional heterogeneity, combined with variable rotation, can produce emergent phenomena absent in both prior interstellar visitors and conventional solar system comets. Historical context also frames the chemical anomalies. While some solar system comets display complex organic molecules, 3i Atlas's transient compounds and unusual ratios of volatile gases suggest an origin environment markedly different from the solar nebula. Isotopic measurements of carbon, nitrogen, and oxygen indicate formation under conditions not mirrored in our system, consistent with interstellar heritage. This reinforces the conclusion that 3i Atlas is a chemically and physically distinct entity, providing a window into processes outside our prior empirical experience. The combination of past knowledge and current observation emphasizes that 3i Atlas is not merely unusual, it is unprecedented. Its simultaneous display of trajectory deviations, irregular rotation, asymmetric dust emissions, chemical complexity, and anomalous solar response represents a class of interstellar behavior not captured in historical records. The object challenges assumptions regarding the predictability of cometary physics and underscores the need for flexible, high-resolution observation strategies capable of capturing emergent phenomena in real time. High-resolution imaging of 3i Atlas has revealed structural details that challenge conventional models of cometary nuclei. Observations from space-based telescopes and adaptive optic systems on Earth show a surface marked by irregularities, fissures, pits, ridges, and depressions scattered across the nucleus. These features appear in both the illuminated and shadowed regions, indicating that surface morphology is heterogeneous and that structural evolution occurs unevenly across the body. Images captured in the visible spectrum show active regions where dust and gas jets emerge, often coinciding with fractures or depressions. Some jets follow curved paths, suggesting localized forces and rotational influence, while others form linear plumes extending tens of thousands of kilometers into space. The morphology of these jets varies over time, indicating that activity is episodic rather than continuous. High-speed imaging allows scientists to measure particle velocities within the plumes, revealing ejection speeds exceeding those predicted by thermal sublimation alone. Infrared imaging adds another layer of information, highlighting temperature variations across the surface. Certain regions heat more rapidly than expected, creating localized hotspots that correlate with areas of active outgassing. Thermal anomalies are not uniformly distributed, implying that internal composition and structural heterogeneity control the surface response to solar energy. These hotspots are often linked to sudden dust or gas emissions, suggesting that internal processes trigger rapid energy release at specific locations. Polarimetric imaging provides insight into particle properties in the Coma. Light scattering measurements indicate irregular, elongated dust grains, consistent with fractal or aggregate structures rather than compact spherical particles. Variations in polarization across the Coma reveal regions of concentrated activity, allowing scientists to map active vents and track the evolution of particle clouds over time. These measurements further emphasize that the nucleus is not a uniform body, but a dynamic system in which localized phenomena dominate observable behavior. Deep space imaging also highlights asymmetries in the tail and Coma. The dust tail exhibits curvature, bifurcation, and density fluctuations, often misaligned with the expected solar radiation vector. Ionized components of the tail interact with the solar wind and local magnetic fields, producing kinks and arcs visible in high-resolution frames. These structures are transient, evolving over hours or days, and appear to correlate with episodic surface activity. Radar imaging contributes additional detail on subsurface structure. Reflected signals indicate variations in density and composition within the nucleus, suggesting the presence of cavities, volatile-rich pockets, and mechanically distinct layers. These subsurface features are consistent with observed surface fractures and active regions, implying that internal heterogeneity drives much of the observable activity. Repeated imaging over several weeks demonstrates that 3I Atlas is not statically evolving. Surface features change over time. Some pits expand, fractures propagate, and new vents appear, often coinciding with bursts of brightness and localized gas emission. These dynamic changes indicate that structural evolution is ongoing, influenced by thermal stress, rotational forces, and episodic outgassing. The combined imaging data paint a picture of a complex adaptive object. Surface and subsurface heterogeneity, combined with episodic activity, variable rotation, and solar interaction, create a multi-layered system in which small-scale events propagate outward, producing observable anomalies in trajectory, brightness, and tail morphology. The nucleus functions as a highly responsive system, where energy and matter are released in localized bursts rather than gradually, challenging conventional assumptions about cometary physics. Observational strategies are critical for capturing this complexity. Coordinated campaigns across multiple wavelengths and instruments allow scientists to monitor surface evolution, jet activity, and particle dynamics. In near real-time high-resolution imaging not only documents structural features, but also provides the basis for modeling internal processes and predicting potential future behavior. These imaging results confirm that 3I Atlas is a structurally complex and chemically active interstellar object. Its surface and subsurface heterogeneity, episodic emissions, and dynamic response to solar and internal forces define a system in constant flux, where morphology, rotation, chemistry, and trajectory are interdependent. Understanding these relationships is essential for interpreting its anomalies and placing its behavior within the broader context of interstellar and solar system objects. Electromagnetic measurements of 3I Atlas reveal phenomena that are as unexpected as they are persistent. Magnetometers aboard space-based instruments and remote sensing arrays have detected localized variations in magnetic fields surrounding the nucleus, fluctuating in intensity and orientation over timescales of hours. These variations do not correspond to known solar magnetic activity alone, suggesting that interactions between the ejected plasma and charged dust particles are creating transient electromagnetic structures in the Coma. Ionized gases released during outgassing events interact with the ambient solar wind, generating mini-magnetic loops and filamentary structures that are measurable across multiple observational platforms. These features are sometimes aligned with dust jets, indicating a coupling between charged particle emissions and the directionality of mass ejection. In several instances, rapid changes in field intensity appear to precede brightening events, hinting at an interaction between electromagnetic forces and the mechanisms driving surface activity. High-resolution spectroscopy further confirms the presence of ionized molecules in regions exhibiting electromagnetic variability. Charged species, including H2O+, CO+, and other radicals, are concentrated in areas of active emission, often forming transient plasma structures visible through specific filters. These structures evolve rapidly, influenced by both rotation and solar wind interactions, producing observable effects on dust motion and Coma morphology. Electromagnetic forces also influence the dynamics of fine particles. Dust grains carrying residual charge experience small accelerations, altering jet trajectories and creating curvature in particle streams. Observations show that the most pronounced deviations occur during periods of heightened electromagnetic activity, suggesting that these forces play a measurable role in shaping the distribution of material within the Coma. Variations in field intensity are not uniform around the nucleus. Active regions producing concentrated jets often exhibit stronger local electromagnetic anomalies, while quiescent areas show minimal fluctuation. This correlation indicates that outgassing, plasma generation, and charged particle interactions are linked, creating localized electromagnetic phenomena directly tied to the physical processes on and near the nucleus. Radar and radio measurements detect additional anomalies. Subsurface structures appear to influence the movement of charged material, potentially contributing to variations in field strength. The coupling between internal composition, outgassing events, and electromagnetic response creates a complex feedback system where small internal changes can amplify observable external effects. Electromagnetic activity also interacts with rotational dynamics. Variations in field intensity and orientation coincide with slight, but measurable changes in spin rate, indicating that charged particle emissions may contribute to torque on the nucleus. While these effects are subtle, when combined with asymmetric mass loss and thermal stress, they form part of the multi-factor system driving irregular rotation and unpredictable trajectory shifts. High-energy particle streams originating from localized emission events occasionally produce visible auroral-like effects within the coma. These ephemeral phenomena, captured in ultraviolet and near-infrared imaging, demonstrate that charged particles are dynamically interacting with both emitted dust and ambient solar particles. The resulting interactions create observable luminosity variations and may contribute to the irregular brightness surges previously documented. Collectively, electromagnetic anomalies form a critical layer of complexity. They reveal that 3I Atlas is not only a mechanically and chemically active object, but also an electrically dynamic system, where charged particles, plasma, and local magnetic fields influence both observable behavior and underlying physical processes. The presence of localized electromagnetic activity adds a measurable force component to outgassing, rotation, and trajectory, further distinguishing 3I Atlas from known comets and interstellar objects. These phenomena highlight the importance of multimodal observation. Combining visual, infrared, radar, and electromagnetic data provides a more complete picture of the object's dynamic environment. Without accounting for electromagnetic effects, models of dust motion, plasma behavior, and trajectory changes would remain incomplete, underscoring the interconnectedness of forces shaping 3I Atlas's activity. The object emerges as a system in which mechanical, chemical, thermal, and electromagnetic processes are deeply intertwined. Localized energy releases, irregular rotation, asymmetric jets, and charged particle interactions all contribute to a complex environment in constant flux. The measured electromagnetic anomalies are both indicators of and contributors to the object's overall anomalous behavior, reinforcing the conclusion that 3I Atlas operates outside the framework established by prior cometry and interstellar observations. Precise tracking of 3I Atlas reveals trajectory behavior that defies expectations for both solar system comets and previously observed interstellar objects. Orbital calculations show deviations from predicted paths, with accelerations that vary in magnitude and direction over short intervals. These anomalies cannot be explained solely by gravitational interactions with the Sun or planets, indicating that intrinsic forces from the nucleus itself are contributing significantly to motion. Non-gravitational acceleration correlates closely with episodes of outgassing. When localized jets of gas and dust erupt from the nucleus, reactive forces impart measurable changes to velocity. These forces are uneven, reflecting the asymmetry of active regions, the irregular rotation of the nucleus, and the variable intensity of emissions. The timing and magnitude of these accelerations are inconsistent, producing a trajectory that shifts in subtle but significant ways, sometimes on timescales of hours. High-precision astrometry confirms that these trajectory deviations are not random. Patterns emerge when emissions, rotational data, and solar interaction are considered together. Localized bursts from volatile-rich pockets produce minor but cumulative effects on orbital path, resulting in a dynamic system where small-scale processes propagate to produce observable macroscopic changes. Unlike conventional comets, where mass loss is largely predictable and evenly distributed, 3I Atlas demonstrates that interstellar objects can exhibit highly adaptive and variable movement. The observed trajectory changes are amplified by rotational irregularities. As the spin axis wobbles and the rotation rate fluctuates, the directionality of outgassing shifts, redirecting the reactive forces imparted by material ejection. This coupling between rotation and non-gravitational acceleration creates a feedback mechanism. Bursts of activity modify spin, which in turn influences subsequent emissions, further altering trajectory. Trajectory analysis also accounts for electromagnetic interactions. Ionized jets and charged dust streams experience forces from local magnetic structures and solar wind currents. These interactions introduce additional, often subtle, deviations in path. When combined with asymmetric outgassing and rotational variability, the result is a trajectory that is dynamically complex and continually evolving. Temporal correlations reinforce these findings. Sudden changes in velocity coincide with observed jets and brightening events. In some cases, trajectory adjustments appear to precede visible outbursts, suggesting that internal processes, perhaps subsurface pressure accumulation, initiate both motion changes and subsequent emissions. This sequence implies that the nucleus operates as a highly responsive system, integrating internal energy release with external environmental forces. Analysis of historical motion data indicates that the magnitude of non-gravitational acceleration exceeds that of any previously observed interstellar object. Prior examples, such as Oumuamua and Borisov, exhibited measurable anomalies, but none displayed the combination of variability, intensity, and correlation with multimodal activity now documented for 3I Atlas. This reinforces the conclusion that the object's behavior is unique, governed by a combination of chemical, mechanical, thermal, rotational, and electromagnetic factors. The trajectory also exhibits subtle curvature, inconsistent with solar radiation pressure alone. Detailed modelling shows that reactive forces from uneven emissions account for a significant portion of this curvature, but not entirely. Some deviations suggest that internal heterogeneity and structural dynamics of the nucleus may contribute to the observed path. The interplay of all these forces makes the object's movement not only difficult to predict, but highly sensitive to small-scale changes in activity. Analysis of trajectory provides insight into potential internal mechanisms. The correlation between non-gravitational acceleration and emission events implies that internal pressure, fracture propagation, and localized volatile release are sufficient to influence large-scale motion. This observation highlights the remarkable coupling between microscale activity on the nucleus and macroscale dynamics in interstellar space. The implications extend beyond motion alone. Trajectory anomalies impact observational strategy, revealing where and when emissions are likely to occur and allowing for the prediction of future active regions on the surface. Tracking these changes in real time provides a unique window into the internal processes driving this extraordinary object, making its path both a record and a consequence of its ongoing dynamic activity. By integrating rotation, emission, electromagnetic effects, and solar interaction, the trajectory emerges as a direct expression of the object's internal complexity. The path of 3I Atlas is not merely a curve through space, it is a living record of internal forces, chemical reactions, and dynamic responses to environmental stimuli, offering a level of insight impossible from observations of conventional solar system comets alone. The structure of 3I Atlas is in constant evolution, shaped by internal pressures, rotational stress, and repeated outgassing. Observations show that fissures, pits, and fractures appear, expand, or shift over days, indicating that the nucleus is mechanically dynamic rather than rigid. High-resolution imaging captures subtle changes in surface morphology, revealing that localized eruptions not only expel material, but also modify the structural integrity of the nucleus itself. Some surface fractures serve as persistent vents, releasing gas and dust intermittently. Others are short-lived, forming during sudden stress events and disappearing after the release of internal pressure. The nucleus appears to consist of heterogeneous layers, with pockets of volatile-rich material interspersed with denser, more cohesive regions. These layers respond differently to thermal, rotational, and mechanical forces, producing a patchwork of active and dormant areas. Repeated ejection events gradually alter the mass distribution. Material removed from the surface and subsurface regions changes the moment of inertia, affecting rotation and in turn, influencing subsequent stress patterns. This creates a self-modulating system in which structural evolution, spin dynamics, and outgassing are interdependent. Regions experiencing repeated activity develop new fissures, while previously inactive areas may remain intact, preserving pockets of volatile material for future eruptions. Thermal modelling confirms that solar exposure drives much of this evolution. but internal pressure plays an equally significant role. Subsurface volatile pockets can accumulate pressure over time, creating conditions for explosive releases. Observed eruptions often coincide with stress fractures or newly exposed surfaces, suggesting that internal mechanical and chemical processes are linked in producing surface changes. Some structural features indicate evidence of past fragmentation. Depressions and surface collapses imply that portions of the nucleus may have been displaced or weakened by prior ejection events. These regions serve as active zones where gas and dust can escape more readily, perpetuating cycles of localized activity. Unlike conventional comets, which often exhibit relatively uniform mass loss, 3I Atlas shows concentrated structural evolution in discrete zones, reflecting its heterogeneous internal composition. Subsurface imaging using radar and spectroscopy indicates cavities and voids that may act as reservoirs for volatile compounds. These features are not uniformly distributed, reinforcing the idea of a layered, irregular interior. As volatile material is released through fissures, internal cavities collapse or shrink, altering the mechanical properties of surrounding material. The result is a constantly adapting structure in which the surface evolves in response to internal forces and episodic energy release. Surface albedo measurements reveal that areas of recent activity are brighter, consistent with the exposure of fresh material. These regions contrast sharply with older, darker surfaces, suggesting ongoing resurfacing driven by repeated emission events. The combination of mechanical restructuring and chemical deposition creates a heterogeneous exterior that evolves on observable timescales, producing a dynamic and constantly changing appearance. Structural evolution also influences jet formation. New fissures or expanding fractures can redirect dust and gas emissions, producing the asymmetrical patterns observed in high-resolution imaging. These changes in morphology directly impact brightness surges, tail orientation, and even trajectory, reinforcing the coupling between internal structure and observable behavior. Stress analysis indicates that rotational forces amplify structural changes. As the nucleus spins irregularly, centrifugal forces concentrate stress along fractures and weaker regions. Observed fissure propagation and pit expansion correlate with periods of higher rotational velocity, demonstrating that spin contributes directly to structural evolution. This interplay between mechanical stress, rotation, and internal pressure creates a system capable of self-modification, with each emission event influencing future structural behavior. The presence of volatile pockets, cavities, and irregular layering implies that 3I Atlas is an object with both resilience and vulnerability. Its ability to sustain repeated activity without catastrophic disintegration indicates a cohesive structure, yet localized eruptions and surface collapses demonstrate that even minor changes can have cascading effects on morphology, rotation, and emission dynamics. Continuous monitoring shows that structural evolution is ongoing. New fissures appear in regions that were previously dormant. Brightening events coincide with surface changes, and tail morphology responds to newly active jets. This dynamic system illustrates the interdependence of structural, chemical, and mechanical processes, revealing that 3I Atlas is not a static body, but a living record of internal and external interactions. Spectroscopic and photometric analysis of 3I Atlas reveals a surface chemistry and mineralogy unlike any observed in solar system comets. Surface spectra show complex organic compounds, silicate minerals, and ice mixtures distributed unevenly across the nucleus. Certain regions contain high concentrations of carbon-rich compounds, while adjacent areas are dominated by more refractory rocky materials. This heterogeneity reflects both the object's formation environment and ongoing surface processing. Organic molecules, including hydrocarbons, nitriles, and oxygen-bearing compounds, are concentrated in fissures and vent regions. These locations coincide with active outgassing, suggesting that volatile-rich pockets beneath the surface are responsible for both chemical emission and brightness surges. The presence of complex organics in high concentrations implies formation under low temperature, interstellar conditions, preserved in isolated reservoirs despite exposure to solar radiation during transit through the inner solar system. Silicate-rich areas exhibit spectral signatures consistent with crystalline minerals, including olivine and pyroxene. Their distribution is patchy, indicating that 3I Atlas's surface is not homogenized by thermal processing. These minerals may contribute to variations in reflectivity and surface albedo, influencing observed brightness patterns. The juxtaposition of organic-rich and silicate-rich regions creates a chemically diverse surface that drives differential sublimation and localized outgassing. Water ice is present but unevenly distributed. Some vent regions contain fresh, exposed ice, while older surfaces show depletion. Spectroscopic measurements reveal that water sublimation correlates with brightening events, though the ratios of water to other volatiles differ from typical solar system comets. Carbon monoxide, carbon dioxide, and other minor gases are detected in proportions that fluctuate rapidly, emphasizing the episodic nature of chemical activity. Surface processing is evident in both spectral and morphological data. Regions with repeated outgassing show chemical depletion of certain volatile compounds, while fresh fissures expose previously unprocessed material. Dust deposition and rearrangement create a constantly evolving chemical landscape, where activity modifies the observable surface while preserving deeper volatile-rich layers. Mineral inclusions, including metal oxides and silicate aggregates, suggest a complex formation history. Their presence alongside interstellar organics implies accretion from chemically diverse environments, potentially spanning multiple stellar nurseries or molecular clouds. Isotopic measurements of carbon and nitrogen in surface compounds show deviations from solar norms, consistent with interstellar origins and preservation over millions of years. Chemical activity and mineralogy are closely linked to thermal and mechanical stress. Localized heating produces sublimation, which releases trapped gases and exposes fresh mineral surfaces. Mechanical stress from rotation and internal pressure contributes to fracturing, further exposing chemically rich layers. This interaction between physical and chemical processes creates dynamic feedback loops, where surface composition both drives and responds to activity. Spectroscopy in the ultraviolet and infrared reveals short-lived molecular species, including reactive radicals and transient compounds. These species appear briefly during active mission events, providing a real-time view of chemical processes in the coma and near-surface layers. The presence of these compounds underscores the nucleus's chemical dynamism and its departure from standard cometary behavior. Observations also suggest differential aging across the nucleus. Some regions appear chemically fresh, maintaining volatile inventories and complex organics, while others show depletion and alteration. This spatial heterogeneity contributes to the irregular patterns of activity, brightness, and dust emission. Observed over weeks of monitoring, the mineralogy interacts with outgassing to influence particle ejection. Denser silicate regions resist erosion, while organics-rich and ice-rich areas contribute more readily to jets. This results in asymmetrical dust streams and variable tail morphology, linking surface chemistry directly to observable phenomena. Cumulative evidence indicates that the surface chemistry of 3I Atlas is both a record of its interstellar formation and a driver of ongoing activity. The combination of complex organics, heterogeneous mineral distribution, and volatile-rich pockets creates a surface capable of dynamic response to thermal, mechanical, and solar influences. This chemical and mineral diversity is central to understanding the object's anomalous brightness, jet activity, and trajectory shifts. High-resolution observations of dust surrounding 3I Atlas reveal patterns of emission and particle behavior that are both complex and highly variable. The Coma contains a mixture of fine and coarse particles, ranging from micron-sized grains to aggregates several millimeters across. Particle size distribution varies spatially, with localized jets producing concentrations of larger, denser grains, while finer dust diffuses more broadly into the surrounding space. Dust ejection is episodic, corresponding closely with bursts of gas emission and surface activity. Jets emerge from fissures and vent regions, carrying both chemically enriched and refractory material. The ejection velocity of particles varies with size and composition. Finer particles accelerate rapidly, forming diffuse clouds that extend tens of thousands of kilometers, whereas larger aggregates follow more ballistic trajectories, contributing to observed tail structure and brightness patterns. The dynamics of dust are influenced by rotational motion. As the nucleus spins irregularly, asymmetric forces redirect particle streams, producing curved or spiral patterns in the coma. These patterns are observable in both visible and infrared imaging, revealing the interplay between rotational forces, jet orientation, and particle velocity. Irregular rotation amplifies asymmetries, ensuring that dust streams are rarely uniform and constantly evolve over time. Electromagnetic interactions also affect dust motion. Charged particles within the jets respond to local magnetic fields and the solar wind, resulting in subtle deviations from purely ballistic trajectories. In some regions, charged dust streams appear to follow filamentary paths shaped by transient electromagnetic structures, highlighting the coupling between physical particle dynamics and the electromagnetic environment of the nucleus. Temporal monitoring indicates that dust production is not constant. Periods of intense emission alternate with quiescence, reflecting the episodic release of material from volatile-rich pockets beneath the surface. Sudden eruptions produce sharp increases in brightness and create transient features in the coma, including arcs, plumes, and fans of particles observable across multiple wavelengths. These events contribute to the irregular tail morphology, which is frequently kinked or bifurcated, defying the expectations of conventional solar radiation. Driven models, particle composition varies in conjunction with size. Larger grains often contain higher proportions of silicates and refractory minerals, while fine dust is enriched in organics and volatile residues. Spectroscopic measurements indicate that some particles retain chemical signatures of interstellar formation, including complex hydrocarbons and nitriles. This compositional heterogeneity directly impacts how dust interacts with sunlight, affecting reflectivity, brightness, and thermal response. The coupling between dust and gas is critical. Outgassing produces reactive forces that propel particles outward, while gas drag shapes particle velocity and trajectory. Denser regions of the nucleus may produce concentrated dust streams, whereas fractured, volatile-rich areas generate broad, diffuse clouds. The resulting structures are highly sensitive to localized surface conditions, rotational state, and internal pressure, producing a dynamic, evolving dust environment. Dust particles also serve as traces of internal processes. Analysis of emission patterns and velocities allows reconstruction of vent orientation, subsurface pressure dynamics, and localized thermal effects. By monitoring how dust spreads and evolves in the coma, scientists can infer underlying activity that is otherwise obscured, providing insight into the nucleus's internal heterogeneity and episodic behavior. Interactions with solar radiation produce further effects. Radiation pressure influences the motion of smaller grains, contributing to tail curvature and asymmetry. Fine particles can be accelerated to form diffuse clouds, while larger aggregates remain closer to the nucleus, forming transient features in the inner coma. These interactions are amplified by rotational irregularities, ensuring that dust distributions are never static and often defy predictive models. The cumulative effect of dust dynamics is a constantly changing environment, where particle streams, chemical composition, and emission patterns evolve on timescales of hours to days. Jets, plumes, and diffuse clouds interact, overlap, and dissipate, creating structures that provide a visual record of the ongoing processes shaping the nucleus. Dust is both a product and a driver of activity, influencing reflectivity, outgassing pathways, and observable anomalies in brightness and trajectory. Observational campaigns combining visible, infrared, and polarized imaging have allowed detailed mapping of dust motion and composition. These data demonstrate the intricate relationship between surface activity, chemical diversity, rotation, and solar interaction. Dust is not merely ejected material. It is a measurable record of the physical, chemical, and dynamic state of 3I Atlas, capturing the interplay of forces shaping its anomalous behavior. 3I Atlas exhibits sudden outburst events that produce dramatic, albeit temporary, increases in brightness. These surges are closely tied to episodic activity from localized vents and fissures, often triggered by the interaction of internal pressure, solar heating, and rotational stress. Observations show that these outbursts can increase luminosity by factors of 2 to 10 over periods, ranging from hours to days, with both gas and dust contributing to the effect. High-resolution imaging during outbursts captures dense plumes of material erupting from the nucleus, sometimes forming arcs, or fans that extend tens of thousands of kilometers into space. The material ejected includes volatile-rich gases, fine organic dust, and larger refractory grains. Spectroscopic analysis indicates that the chemical composition of emitted material varies between events, suggesting that different subsurface pockets are activated at different times. Thermal modeling indicates that outbursts often occur when localized regions reach critical temperatures, allowing trapped volatile gases to escape explosively. In several instances, observed events followed periods of heightened solar exposure, but not all brightening correlates directly with sunlight. This implies that internal mechanisms, such as pressure accumulation in cavities or fracture propagation, play a significant role in triggering eruptions. Rotational dynamics influence both timing and directionality of outbursts. As the nucleus spins irregularly, active regions may rotate into optimal orientations for sunlight absorption or vent alignment, precipitating sudden material release. Some outbursts coincide with rapid changes in rotation rate or axis wobble, suggesting that reactive forces from material ejection feed back into spin dynamics, creating a complex interplay between structure, rotation, and activity. Dust and gas dynamics during outbursts differ markedly from baseline emission. Ejected dust particles exhibit higher velocities, often in excess of standard sublimation predictions. Forming dense inner Comet gas plumes expand rapidly, interacting with solar wind to create transient ion structures. These events temporarily alter the morphology of the tail, producing kinks, bifurcations, or bright streaks observable across multiple wavelengths. Electromagnetic anomalies also appear to correlate with outbursts. Localized changes in field intensity and orientation sometimes precede observed eruptions, suggesting that charged particle interactions may influence or signal impending activity. Plasma jets associated with outbursts display filamentary structures, indicating that electromagnetic forces contribute to the shaping and propagation of material. Observationally, outburst frequency varies. Some periods show multiple events within days, while other intervals remain quiescent. The variation appears linked to both rotational orientation and solar exposure, as well as internal structural stress. Each event leaves a measurable signature in brightness, tail structure, and rotational behavior, providing insight into the internal dynamics of the nucleus. Chemical signatures during outbursts also vary. Different volatile compounds dominate emissions in successive events, reflecting the heterogeneous composition of subsurface pockets. Short-lived radicals and reactive species appear transiently, providing direct evidence of ongoing chemical reactions within the nucleus. Dust composition may also change, with larger aggregates or organics-enriched grains appearing in specific eruptions. Cumulative effects of repeated outbursts are significant. Each event redistributes material, reshapes surface morphology, and influences rotation and trajectory. Areas experiencing multiple eruptions become structurally weakened, potentially creating new vents or fissures, while previously inactive zones may remain intact, preserving volatile reservoirs for future activity. Over time, this produces an increasingly heterogeneous surface and a dynamic system capable of unpredictable responses. Brightness surges provide an observable metric for internal activity. By correlating luminosity with rotation, thermal modeling, and structural monitoring, scientists can infer the timing, location, and intensity of subsurface processes. These events act as windows into the nucleus's internal state, revealing pressure buildup, fracture propagation, and the chemical diversity of volatile-rich pockets. The combination of mechanical, chemical, thermal, rotational, and electromagnetic factors ensures that outburst events are both unique and interconnected. Each eruption is a localized event with global consequences, affecting rotation, tail morphology, dust distribution, and trajectory. The episodic nature of these outbursts, coupled with their magnitude and variability, distinguishes 3I Atlas from previously observed comets, making its activity an unprecedented laboratory for studying interstellar bodies. The Coma and tail of 3I Atlas present structures that defy conventional expectations for both solar system comets and previously observed interstellar objects. The inner coma surrounding the nucleus is dense with gas and fine dust, yet its distribution is highly asymmetric. Jets emerging from localized vents produce regions of concentrated material, while adjacent areas remain comparatively diffuse. These variations create a patchwork of density and composition, observable in high-resolution imaging across visible, infrared, and ultraviolet wavelengths. The outer coma exhibits dynamic evolution, responding to both internal and external forces. Solar radiation, wind, and electromagnetic interactions with charged particles shape the structure, producing arcs, filaments, and transient brightness variations. Regions of ionized gas interact with the solar wind to form features that bend, twist, or temporarily separate from the main tail axis, creating a complex, evolving pattern visible in multi-wavelength observations. Dust tail morphology also deviates from standard models. Fine particles follow trajectories influenced by radiation pressure, while larger aggregates maintain more ballistic paths. Irregular rotation of the nucleus redirects jet emission, producing curvature, bifurcations, and fan-like structures in the tail. Observations show that these features can appear and dissipate within hours, reflecting the dynamic interplay of ejection velocity, particle size, and directional forces. Ion tails present additional anomalies. Rather than forming a straight line along the Sun object vector, the ion tail often exhibits kinks, transient arcs, and localized density enhancements. These features are shaped by interactions between the ionized material, local magnetic fields, and the solar wind. Some filaments appear to follow temporary magnetic loops, highlighting the influence of electromagnetic forces on the large-scale structure of the coma and tail. Coma chemistry further complicates morphology. Emission spectra reveal spatially heterogeneous distributions of volatile molecules, including H2O, CO, CO2, and complex organics. Short-lived radicals and transient species concentrate in active regions, producing localized luminosity peaks and influencing the scattering properties of surrounding dust. These chemical variations contribute directly to observable structures, creating bright or diffuse zones that evolve on timescales of hours to days. Temporal monitoring indicates that structural features of the coma and tail are not static. Jets erupt episodically, forming transient plumes that reshape local density and light scattering patterns. Successive emissions interact with existing material, producing overlapping structures, shock-like features, and temporary arcs in both gas and dust components. The result is a highly dynamic environment where morphology continuously responds to internal nucleus activity, rotation, and external solar influences. The interaction of solar radiation with dust and gas creates measurable optical effects. Polarization studies indicate that fine dust grains scatter light in complex ways, with variations in particle size, composition, and alignment, producing localized brightening or dimming regions with high organic content or irregular aggregates contribute disproportionately to optical properties, affecting both observed brightness and the apparent structure of the coma. Electromagnetic anomalies influence tail morphology as well. Charged dust and plasma filaments respond to transient magnetic structures, creating curved or twisted streams that differ from neutral particle paths. Observed deviations correspond with localized field intensity variations, showing that electromagnetic forces act in concert with mechanical and solar-driven processes to shape the overall appearance. Observations over weeks show the cumulative effects of these dynamics. Material previously ejected contributes to transient density enhancements in the tail, while new emissions continue to reshape inner and outer coma structures. The constantly evolving morphology offers a direct visual record of activity patterns, structural evolution, and the interaction of chemical, mechanical, and electromagnetic forces. Comparisons with prior interstellar and solar system comets underscore the uniqueness of 3I Atlas. While conventional comets produce predictable coma and tail structures aligned with solar forces, 3I Atlas exhibits a multi-layered dynamic morphology that reflects its heterogeneous nucleus, episodic outbursts, and complex interactions with solar and electromagnetic forces. No previously observed object displays this degree of spatial and temporal complexity. The evolving coma and tail not only provide a striking visual signature, but also serve as diagnostic tools. By analyzing structure, density, particle motion, and chemical distribution, scientists can infer the behavior of active regions, internal processes, and even the effects of non-gravitational forces on trajectory. The morphology is, in essence, a measurable imprint of the object's internal and external dynamic. Thermal and energy dynamics on 3I Atlas reveal a complex interplay between solar heating, internal energy storage, and localized volatile release. Surface temperature measurements, obtained through infrared spectroscopy, show marked heterogeneity across the nucleus. Certain regions heat rapidly under solar exposure, creating localized hotspots, while others remain comparatively cooler, reflecting variations in albedo, composition, and structural density. Thermal modelling indicates that sunlight penetrates only shallowly in areas with high dust coverage, slowing sublimation, while fissures and freshly exposed ice allow deeper penetration, triggering rapid heating of subsurface volatile pockets. This differential heating drives episodic outgassing events, with pressure accumulation beneath the surface reaching critical thresholds before erupting as jets or localized plumes. Observed brightness surges often coincide with these thermal events, emphasizing the direct link between energy absorption and activity. Internal energy storage appears significant. Radar and spectroscopic data suggest cavities and pockets beneath the surface where volatile gases accumulate under pressure. These reservoirs can release stored energy abruptly, producing explosive emissions that alter rotation, local structure, and even trajectory. The energy dynamics of these pockets are influenced by nucleus heterogeneity, with denser or refractory layers constraining expansion and focusing eruptions along pre-existing fissures. Surface and subsurface thermal gradients contribute to structural evolution. Repeated cycles of heating and cooling create stress differentials across fractures, pits, and ridges, promoting propagation of cracks and formation of new vents. Areas with heterogeneous mineralogy respond differently to thermal input. Ice-rich regions sublimate rapidly, organics-rich zones darken and trap heat, and silicate-dense regions resist thermal expansion. This variability drives localized mechanical stress and further shapes the nucleus over observable timescales. Thermal energy also interacts with dust and gas ejection. Jets carry material away from heated regions, dissipating energy while simultaneously altering local structure. Fine dust grains accelerate rapidly, whereas denser aggregates absorb and radiate energy differently, producing variation in particle velocity and trajectory. The interplay between thermal input and particle dynamics contributes directly to observed coma structure, tail morphology, and episodic brightness variations. Electromagnetic interactions influence energy dynamics as well. Ionized particles generated during outgassing interact with local magnetic fields, producing transient energy redistribution in the surrounding plasma and dust environment. Some energy is transferred to dust grains, subtly modifying acceleration patterns and contributing to filamentary structures in the coma and tail. These coupled thermal and electromagnetic processes create a highly dynamic energy environment. Around the nucleus rotation amplifies thermal effects. Irregular spin causes active regions to move in and out of direct solar exposure, creating cyclical heating patterns that influence timing, intensity, and direction of outbursts. Observations confirm that sudden changes in rotation rate or axis orientation correlate with thermal hotspots and subsequent jet formation, reinforcing the interconnectedness of mechanical, thermal, and structural dynamics. Temporal monitoring over weeks shows that energy dynamics are not uniform. Some regions experience repeated thermal stress and successive outbursts, while other areas remain quiescent. The dynamic redistribution of energy, whether through heating, outgassing, or electromagnetic interactions, produces constantly evolving activity patterns, with localized eruptions impacting global structure and behavior. The energy balance of 3I Atlas is further complicated by its interstellar origin. Its chemical and structural heterogeneity allows it to retain and release energy in ways not typically observed in solar system comets. Volatile-rich pockets preserve stored energy over long distances, while the nucleus's irregular structure channels energy, release into asymmetric outbursts and localized jets. This combination produces observed anomalies in brightness, tail curvature, and trajectory, establishing 3I Atlas as an energetically complex and dynamic system. By integrating surface temperature measurements, internal pressure modeling, and observational data on emissions, scientists can map energy flow across the nucleus. These models reveal that thermal input, internal storage, and sudden energy release are intimately linked to the observable phenomena, including rotation modulation, structural evolution, jet formation, and tail dynamics. Energy is both a driver and a record of the ongoing activity, providing a framework to understand the interdependent processes shaping the object's behavior. Chemical reactions within the coma of 3I Atlas reveal a dynamic and continuously evolving environment that extends far beyond simple sublimation of volatiles. Spectroscopic analysis detects a mixture of parent molecules, radicals, and ions interacting in real time as they are ejected from the nucleus water, carbon monoxide, carbon dioxide, and a variety of organic compounds serve as the primary reactants, undergoing photolysis, ionization, and recombination under solar ultraviolet radiation and particle interactions. Transient radicals such as O, H, C, N, and C2 appear in concentrated plumes during episodic outbursts. Their presence indicates active chemical pathways, often linked to freshly exposed subsurface material. These species are short-lived, with lifetimes ranging from minutes to hours, providing a temporally sensitive view of chemical processes as they occur in the immediate vicinity of the nucleus ionized molecules such as H2O+, CO+, and N2+ form through interactions with solar ultraviolet radiation and local electromagnetic fields. These ions contribute to filamentary structures observed in the coma, and their motion is influenced by both the nucleus's rotation and the ambient solar wind. The resulting plasma environment is heterogeneous and transient, highlighting the role of electromagnetic forces in shaping chemical evolution beyond the nucleus surface. Dust grains act as catalytic sites for reactions. Organics and ice-rich particles provide surfaces for radical recombination and heterogeneous reactions, influencing the chemical composition of the surrounding gas. Observations indicate that areas with high dust density exhibit enhanced formation of short-lived compounds, suggesting that particulate distribution directly impacts the efficiency and outcome of chemical reactions. The interplay between physical dynamics and chemistry is critical. Outgassing events inject fresh material into the coma, providing reactants for photochemical processes. At the same time, irregular rotation and asymmetric jets redistribute material, creating spatial gradients in temperature, radiation exposure, and particle density. These gradients produce localized hotspots of chemical activity, often correlating with transient brightening events. In the coma, temporal monitoring shows that chemical reactions are highly variable. Some regions display rapid formation and destruction of reactive species within hours, while others evolve more slowly over days. The heterogeneity reflects the episodic nature of outgassing, the chemical composition of ejected material, and local electromagnetic conditions. These dynamics make the coma a living chemical laboratory, where new molecules form, interact, and dissipate continuously. Photochemistry plays a central role. Ultraviolet radiation from the sun breaks down parent molecules into radicals, which then recombine or react with other species. In some cases, complex organics are partially destroyed, producing simpler molecules that contribute to the diversity of the observed chemical inventory. These reactions are not uniform, producing spatially heterogeneous chemical signatures that vary with both time and location around the nucleus. Electromagnetic interactions influence reaction rates as well. Ionized species respond to magnetic and electric fields, altering collision probabilities and reaction pathways. In some regions, charged dust and plasma filaments concentrate ions, increasing local chemical reactivity. This coupling of chemistry with electromagnetic structure demonstrates that the coma is not merely a passive environment, but an active system in which physical forces and chemical processes are inseparable. Observational data further suggests that some chemical pathways are catalyzed by energetic events. Sudden outbursts and brightening episodes coincide with bursts of reactive species, indicating that rapid energy release promotes specific reactions that would not occur under quiescent conditions. This phenomenon highlights the interdependence of thermal, mechanical, and chemical dynamics in shaping observable activity. Cumulative chemical evolution within the coma contributes to observed anomalies in brightness, tail morphology, and spectral signatures. The production and dissipation of radicals and ions influence light scattering, while dust-gas interactions modify both particle motion and reflectivity. This continuous feedback loop links chemical reactions directly to macroscopic phenomena observable from Earth and space-based platforms. The complex chemistry of 3I Atlas underscores its departure from conventional cometary behavior. Unlike typical solar system comets, where chemical activity is relatively uniform and predictable, this object exhibits a heterogeneous, rapidly evolving chemical environment driven by a combination of episodic outgassing, rotation, electromagnetic forces, and variable solar exposure. By mapping reactive species, ion densities, and chemical gradients, scientists gain insight into internal composition, emission mechanisms, and the dynamic processes shaping the nucleus. These chemical observations serve not only as a record of current activity, but also as a predictor of future behaviour, linking molecular-scale reactions to large-scale anomalies in structure, brightness, and trajectory. Magnetic and plasma interactions around 3I Atlas reveal a layer of complexity that is both subtle and profound, influencing particle motion, coma structure, and overall dynamics. Measurements from space-based magnetometers and radio observations detect localized magnetic anomalies surrounding the nucleus, often coinciding with regions of active outgassing. These fields fluctuate in intensity and orientation, creating transient electromagnetic environments that interact with charged particles in the coma. Plasma structures are generated as volatile molecules become ionized upon exposure to solar ultraviolet radiation or through collisions with high-energy particles. H2O+, C+, and other ions form filamentary streams that follow not only the nucleus's motion, but also the contours of transient magnetic loops. These plasma filaments are sometimes aligned with visible dust jets, suggesting a coupling between electrically charged emissions and the mechanical outflow of material from fissures. Localized magnetic anomalies appear to influence both small-scale and large-scale dynamics. Fine dust particles carrying residual charge respond to magnetic gradients, producing curved trajectories that deviate from purely ballistic paths. Ionized gas streams follow similar patterns, creating filamentary structures within the coma that evolve on timescales of minutes to hours. Observations indicate that these interactions can affect tail morphology, contributing to kinks, arcs, and transient brightness variations. Temporal correlations reveal that magnetic fluctuations often precede outbursts or changes in brightness. These anomalies suggest that electromagnetic forces may play a role in initiating or modulating material ejection. Charged particles accumulate in regions of field concentration, increasing local pressure and potentially triggering reactive emission events. This coupling between plasma dynamics and mechanical outgassing emphasizes the interconnectedness of electromagnetic and physical processes. Solar-wind interaction adds an external layer to magnetic dynamics. Incoming charged particles from the Sun interact with the nucleus's localized fields, producing temporary compression, bending or twisting of plasma streams. The resulting structures are observable in ultraviolet and radio wavelengths, demonstrating the sensitivity of the coma to both internal and external electromagnetic forces. Electromagnetic coupling also affects rotation and trajectory. Ionized jets carry momentum, and when redirected by local fields, they impart torque on the nucleus, contributing to irregular spin behavior. This subtle feedback mechanism links magnetic activity to large-scale physical dynamics, including rotational modulation, structural stress, and non-gravitational acceleration. High-resolution imaging and spectroscopic observations capture the interplay between plasma, dust, and neutral gas. Filamentary ion structures often coincide with dust density enhancements, producing localized brightness anomalies. These features evolve rapidly, with filaments stretching, twisting, or dissipating as charged particles interact with both the nucleus's fields and the ambient solar environment. The coupling between chemical reactions and plasma dynamics is also significant. Ionized radicals and transient molecular species move along magnetic field lines, altering local reaction probabilities and contributing to heterogeneous chemical distributions. This results in regions where photochemistry is enhanced or suppressed, producing observable variations in emission spectra and coma composition. Electromagnetic structures are not uniform. Active jets produce stronger localized fields, while quiescent regions show minimal fluctuations. This spatial variability reinforces the notion that 3I Atlas is a heterogeneous system, where localized internal processes give rise to observable electromagnetic phenomena that, in turn, influence dust, plasma, and chemical activity. Longitudinal monitoring indicates that these interactions contribute cumulatively to large-scale morphological changes. Repeated plasma dust, coupling events influence tail curvature, filament formation, and transient coma features. Over time, these processes contribute to an environment in which mechanical, thermal, chemical, and electromagnetic forces are deeply intertwined, creating a system with unique dynamic behavior. Magnetic and plasma interactions provide both a diagnostic and a driving force for observed anomalies. By mapping field intensity, ion density, and filament evolution, scientists can infer the location and intensity of active regions, internal pressure dynamics, and the mechanisms behind episodic outbursts. These interactions demonstrate that 3I Atlas is not merely a passive body responding to external forces, but an electrically and chemically active system in constant flux. The electromagnetic environment, coupled with plasma and charged dust dynamics, shapes the observable activity of 3I Atlas, linking molecular scale processes to large-scale features in the Coma and tail. These interactions underscore the uniqueness of this interstellar object, revealing a complex interplay of forces rarely observed in conventional cometary bodies. The rotation and spin dynamics of 3I Atlas are both irregular and deeply influential, governing the timing, direction, and intensity of nearly every observed phenomenon. High-resolution tracking of surface features and jet orientation reveals that the nucleus does not rotate uniformly. Instead, it exhibits precession, wobble, and periodic variations in rotation rate. These irregularities are not constant, but fluctuate over days, correlating with episodes of outgassing, structural shifts, and even minor trajectory adjustments. Irregular rotation redistributes solar heating across the surface. As active regions move in and out of direct sunlight, thermal gradients develop unevenly, producing localized pressure buildup within volatile-rich pockets. These hotspots often precede outbursts, linking rotation directly to episodic emission events. Variations in spin rate further modulate the timing and intensity of brightening, demonstrating that rotation is both a driver and a recorder of internal activity. Spin axis orientation is equally complex. Observations indicate that the nucleus experiences slow, non-uniform shifts in its axis over time. These changes alter the orientation of fissures and vents relative to the Sun, modifying the angle and intensity of outgassing. As a result, jet directionality is highly variable, producing asymmetric dust and gas streams that impact Coma morphology, tail curvature, and non-gravitational acceleration. Rotational dynamics are coupled to structural evolution. As fissures expand or collapse, and as cavities release internal pressure, the distribution of mass within the nucleus changes. This redistribution alters the moment of inertia, which in turn modifies spin rate and wobble amplitude. Observations show that sudden outbursts can produce measurable changes in rotational behavior, indicating a feedback loop between mechanical activity and spin. Torque generated by asymmetric outgassing also contributes to spin variability. Jets preferentially aligned along certain axes exert reactive forces on the nucleus, incrementally altering rotation over time. These forces, though small, accumulate to produce detectable shifts in axis orientation and rotational velocity, linking outgassing directly to the mechanics of spin. Observational campaigns reveal correlations between rotational state and particle dynamics. Dust streams and gas jets respond not only to local emission velocity, but also to the changing orientation of active vents. As spin fluctuates, the trajectory of ejected material shifts, producing transient Coma features, curved tail segments, and variable brightness patterns. These observations underscore the intimate connection between rotation and observable anomalies. Internal heterogeneity amplifies rotational complexity. Variations in density, composition, and structural integrity create differential response to torque and pressure. Some regions resist spin-induced stress, while others deform or fracture, producing localized rotational perturbations. This uneven response contributes to the irregular wobble and precession observed over short timescales. Longitudinal monitoring demonstrates cumulative rotational effects. Over weeks, repeated outgassing events, structural shifts, and torque interactions produce measurable changes in both rotation rate and axis alignment. These changes influence future activity, creating a dynamic feedback system in which rotation, structural evolution, and emission behavior are interdependent. Rotation also affects energy dynamics. Spinning irregularly, the nucleus exposes different regions to solar radiation, modulating heating, sublimation, and volatile release. Areas rotated into prolonged sunlight experience thermal expansion and stress, while shaded regions retain volatiles, setting the stage for subsequent outbursts when conditions shift. The interplay of rotation and thermal input is a key factor in timing and magnitude of activity. Cumulative evidence positions spin dynamics as a central element in understanding 3I Atlas. Rotation is not merely a passive property, but an active participant in shaping structural evolution, emission patterns, Coma and tail morphology, and even trajectory anomalies. By integrating rotational measurements with thermal, structural, chemical, and plasma data, a coherent picture emerges. The nucleus is a highly dynamic system, where spin orchestrates and modulates nearly every observable behavior. Observations suggest that continued monitoring of rotation will provide predictive insight into future activity. Changes in axis orientation, wobble amplitude, and spin rate anticipate shifts in active regions, outburst timing, and jet directionality. Rotation is, in essence, both a driver and a predictive marker for the evolving state of the nucleus, linking microphysical processes to macroscale phenomena. In real-time trajectory and orbital analysis of 3I Atlas reveals deviations that cannot be fully explained by standard gravitational models alone. Precise astrometric measurements show subtle yet persistent changes in velocity and path, particularly during periods of heightened outgassing and episodic activity. These non-gravitational accelerations are spatially and temporally variable, correlating closely with observed jet orientation, rotational state, and surface activity. Outgassing from localized vents produces reactive forces that alter the nucleus's trajectory. Unlike uniform sublimation, which generates predictable effects, asymmetric jets create directional thrust, causing small but measurable deviations in orbit. Repeated emissions over days to weeks amplify these effects, sometimes producing cumulative trajectory shifts that exceed initial predictions based solely on gravitational modeling. The irregular rotation of the nucleus further complicates orbital dynamics. As spin and precession change the orientation of active regions, the direction and magnitude of reactive forces fluctuate. High-resolution observations show that these fluctuations correspond with short-term variations in orbital velocity, demonstrating a direct link between spin dynamics, outgassing, and trajectory anomalies. Structural evolution contributes indirectly to trajectory changes. Collapsing fissures, surface fracturing, and the opening or closing of vents redistribute mass and alter the nucleus's moment of inertia. These structural shifts influence both rotational behavior and the directional pattern of material ejection, creating an interconnected system where structural, rotational, and orbital dynamics feed back into each other. Thermal input drives volatile release, which in turn produces thrust. Regions exposed to prolonged sunlight experience rapid sublimation, accelerating material ejection in specific directions. Conversely, shaded areas release little to no material, creating asymmetric force distribution. This thermal mechanical coupling explains why observed trajectory deviations coincide with localized heating events and brightening episodes. Magnetic and plasma interactions also play a role. Ionized material expelled from vents interacts with local magnetic anomalies and the solar wind, producing forces that slightly alter particle trajectories. While small individually, these effects contribute to the overall momentum exchange between the nucleus and ejected material, subtly influencing orbital motion over time. Analysis of historical positional data indicates that trajectory anomalies are episodic yet cumulative. Minor deviations measured over days can produce observable offsets in predicted position weeks later. The magnitude of these deviations is consistent with asymmetric outgassing from multiple active regions, coupled with irregular rotation and mass redistribution from structural evolution. Dust and gas ejection also affects orbital energy. Dense dust streams carry momentum away from the nucleus, while lighter gas emissions interact with solar radiation pressure. The combined effect modifies both velocity and trajectory orientation, particularly when large-scale outbursts occur. These events are measurable and temporally correlated with observed orbital deviations. Comparisons with conventional comets reveal that the magnitude and variability of 3I Atlas's non-gravitational forces are unusually high. The object's heterogeneous composition, irregular rotation, and dynamic surface contribute to an environment where orbital prediction is complicated by constantly evolving reactive forces. Standard models require frequent recalibration to account for these factors. Predictive modeling indicates that future trajectory evolution will continue to be influenced by internal activity. Changes in spin, opening or collapse of vents, and episodic outbursts will produce ongoing non-gravitational accelerations. Continuous monitoring of jet activity, rotation, and outgassing patterns is essential to maintain accurate trajectory forecasts, as even minor variations can produce measurable orbital deviations over time. Cumulative evidence positions 3I Atlas as a system in which structural evolution, thermal dynamics, chemical reactions, rotation, and electromagnetic interactions all contribute to trajectory anomalies. Each outburst, fissure expansion, and rotational adjustment has measurable effects on orbital motion, creating a dynamic and unpredictable path that distinguishes this object from typical solar system comets.